Okay, so SI5. So, right, so I mean, look, we're thinking surface independence is a likely, I mean, given where we are in it, right? So, nevertheless, the point is what we're trying to compute flux. We have a vector field given. We have a surface given, and this is a weird looking surface. Let's see here. X plus, okay, either, ooh, man. Actually, let's see, wait a second, I'm a little concerned here. Now, what does this look like? So, z is x to the fourth plus e to the y squared. So, well, if you think about how z depends on x and y separately, I mean, as it depends on x, it's x to the fourth, so it's curving up. It's sort of kind of parabolic, but more so in the x direction. And e to the y squared is even more than that, right? It's another sort of increasing on each side. So roughly speaking, now this is not exactly accurate, but roughly speaking, this is going to be kind of a parabolic, like sort of a kind of a, looks a lot like a paraboloid. And now my concern is I see that I have x plus y plus z less than or equal to 0. And I think I was just being sloppy there. I think I must have meant x plus y plus z less than or equal to 1. Because that plane goes through the origin, and it's not clear that that angled plane necessarily intersects with this surface at all. I think this is a typo in the problem. So let's change this problem right now. I'm going to send an email announcement out to everybody, and I'm going to make a change in the book for the future, but for the moment, just scratch that out and make that a 1. Okay? Because we really need to do that for this problem. Okay. All right. Let's see here. So now what does that tell us then? Well, now the plane now is some sort of it goes through this point that this weird surface does as well, and as that plane cuts through, it's going to cut off some sort of let's see here. It's going to, well, it's very hard to draw this, but it's going to intersect in some sort of a slice. So let me redraw the picture. The part of that surface that I'm actually interested in is, I mean, that's not a very good picture, but there's kind of it's a little bit of surface, but its boundary curve, let's see here, oriented upward. Yeah, that's right. The boundary curve is in that plane, but the surface kind of hangs down below that because of the shape of this thing. Does it make sense? Okay. Okay, so back to the problem. Now we want to compute the flux of that vector field through this surface. Now we have a strong reason to believe that surface independence is going to come in here. But even if we hadn't, let me just point out, even if we hadn't, how do we compute fluxes? Well, we either use Stokes's curl theorem or use Gauss's divergence theorem. One way or the other, we're going to need to compute divergence. And let's take the divergence then of this vector field. And the divergence of f, well, we need to take the x partial of that. That's minus 2y. The y partial of that is plus 2y. The z partial of that is 0, and you add it up, and you get the divergence is just 0. And since the divergence is 0, we know a lot of things. For one thing, we know that this vector field has an anticurl. We don't know how to find anticurls unless it's really, easy situation. But nevertheless, we know there's an anticurl. We also know that, more importantly, that this vector field is surface independent. So I can take this surface back here, and I can say I can take any surface that has the same boundary, and I would much rather consider the flat surface there in this plane that has that same boundary curve. Does that make sense? Okay. All right, and good news, this normal vector is easy to write down. I mean, the plane is x plus y plus z is less than or equal to, or the plane is where it's equal to 1. So that means that this normal vector I can just take as 1, 1, 1. And therefore, for my unit normal vector, I can take 1, 1, 1 over the square root of 3. Right? Okay. Right. So I can rewrite my flux then. So I've got a new surface. It's a nice, pretty surface. And we're doing flux through the, let me call that surface S2. So flux through S2, F dot N ds. And we'll see that dot product, well, we're going to have a square root of 3 that's going to be in all the terms. But other than that, we're just taking the vector field and multiplying all the terms, all the components by 1 and adding them up. And so what I'm going to get then is, well, let's see. Let's start adding up terms there. I've got a plus e to the z and a minus e to the z. I've got a minus 2xy and a plus 2xy. I've got a y squared and a minus y squared. That ends up being 0. Does that make sense? This dot product, and so therefore your answer is 0. Yeah. Does that make sense to everybody? So my apologies for the oops on the problem here. This really does need to be just in order to make sure that we know that that there actually is a little bit of surface there. This could have been a swing and a miss, and it's hard to actually tell by looking whether it's a swing and a miss or not. But just make that a 1. And it's definitely not a swing and a miss. And I'll send out an email to the class about that. Any other questions? Okay. Let's see here. Okay, let me stop that.